Okay, so this is the work I'm going to present as work that we did in our 3D understanding group in Rafael. We sit in Jerusalem. The other people working on this was Tavi Halperin and David Anon, also from our group. And what we're going to talk about is segmentation, mostly of images. We're also going to talk about 3D modeling and how that can help us. All right, so the general task here is we have an image up here, which is higher resolution than what you can see. And the task here is to give semantic data to each pixel. We want to say what class it is. And the motivation should be clear to anyone in this conference. Just a few examples for modeling. Polyface talked about that this morning. Obviously, if you know what you're modeling, it can help you understand what the 3D shape should be. Urban navigation, if you want to know where you are, knowing what things are will help. Not bumping into things, it's important to know what's road and what's not. And just one final example is if you want to register to a white map, then obviously pixels are not enough because nothing looks like in the real world like they look in the map. So that's the motivation. It should be clear to everyone. And I've been told that the structure of the talk is a bit confusing, so I'll give you all the spoilers in advance. So the task at hand is we have an image and we want to give it to each pixel. In the beginning, I'm going to talk about how we do that. In a typical case, we use the ISPRS benchmark as a test case. We tweak the loss a bit, so we're going to talk a bit about the F1 loss, and we're going to compare it to the state of the art. And then we're going, in the second part of the talk, I'm going to talk about what the problem is when you want to address the real world, and that's usually creating the data. And so we're going to use the 3D reconstruction to help us do that. And then we'll present the results. So here's the challenge. The ISPRS dataset is that's the International Society for Remote Sensing. It's a catchy name. And on the left, we have one image. It's a very high-resolution image. This image is 6,000 by 6,000 pixels, so it's 36 megapixels, and at a ground resolution of 5 centimeters a pixel. And this is the ground truth labeling, where each pixel is assigned one of the 5 classes or an undefined. Some pixels didn't fit in. And, okay, so I don't know if you can see, there's a lot of data to take in. This is the road. These little blobby areas are vegetation. And here we have the buildings, and these points here are cars, and they're all labeled, very meticulously labeled, all these little cars and the vegetation. And there's also low vegetation and high vegetation, which often look very, very similar. And in this data set, they also assign a height map, a DSM, which was computed from the images. There's actually a whole pipeline behind this image. This isn't the original image. This is an orthophoto created from multiple images using pixel matching, and the DSM is also given. So there are errors in the DSM, and also there are little warpy effects around the discontinuities of height, and that's something that we have to handle. All right, so the state of the art, the way nowadays, in the past couple of years, you would handle this is using a fully convolutional network, and that's what we do. Probably don't need to say a lot of words about fully convolutional network, so we'll do this quickly. A typical network, you have a single input, which is the image, generally either 1 or 3-dimensional, and then as it's pushed through the network, the width and the height is reduced, and the we'll call it the feature representation gets deeper and deeper. So in this specific case, it's 96 and 256. Then it gets deeper for a while until finally we have what sometimes is called the representation, the feature representation for the image. Here, this is already 1-dimensional, so this is just a vector of 4,096 values. And then you have the final classification layer. In this case, there are 1,000 classes, the ImageNet, and where you get a probability distribution between all classes. And in this case, you hope that the highest value you get at the proper class, which is the tabby cat in this case. And just so that there won't be only cats in our, we also have a dog here. So in the convolutional layer, you switch these last layers. Instead of being a fully connected layer where the output is a 1 vector, you look at it also as a convolution. So the input can be any size. And then it also outputs a proportionally sized output. So in this case, it's also 4,906 values deep, but it's proportional to the input width and height. And then the output would be a heat map. So you can think of each patch of 96 pixels would output a single one of these, and obviously they're overlapping, and you do it as a fully convolutional network. And this image is greatly downsampled in this network, specifically by ratio of 1 to 32. And then you somehow have to upsample, and the typical way of doing it would be using skip layers now. This is a network, it's pretty popular now, the fully convolutional networks by Jonathan Long. So that's great. So this is the ground truth, and this is the output, and they look pretty similar. I'll flip through them quickly. Is the image. This is our output. Again, try to focus on something specific, like this little patch here, a bunch of cars, and the buildings and the road. We'll flip through this a bit. If you get dizzy, you can look away. And I'll flip through our results and the ground truth, and they're pretty similar. Try to ignore the red patches, because we don't predict undefined. It just gets a loss function of 0. And a little bit zooming in. Interestingly, in this data set, it's also in the original images and through the projector, it's really impossible to see. There are some trees here along this patch with a background of low vegetation. And so we completely missed that. Our FCN misses that. And this is the ground truth. Also, interestingly, up here, up on the top, this was probably taken in the winter, so there's no foliage on the trees. So you can see the cars through the branches, and they labeled it as vegetation, and that's pretty much what we learned as well. So you'd have to decide one way or another if you see cars through vegetation, what to do with it. Okay, so those are good results, in my opinion, and also not compared to state-of-the-art, just as results. A bit of detail. So we use an F1 loss, which I'll talk about in the next slide. The network has 130 million parameters. We use some data augmentation, cropping the images. Obviously, they're too big to fit onto a GPU, even the Titanics. And we do mirroring of the data, even though that decreases the results on this data set because they've all been taken at the same time. So the shadows are all pointing in the same direction. And mirroring actually loses that information, but we do it anyway because we don't want to overfit on a specific data set. And training time is about 24 hours. So a bit about the F1 loss. The problem with a typical multi-class log loss is that, there was supposed to be some animation here. The problem with a multi-class log loss is that the loss function is defined per pixel in our case, or per data point. And you get a score on that specific question, and then you sum up all your answers over all the questions. Meaning, basically, you want to be as right as possible, as often as possible, for each sample. And that doesn't work very well when on an unbalanced data set. So that works well if 50% of the answers are yes and 50% of the answers are no. The multi-class log loss will work fairly well. On an unbalanced data set where, for example, you're trying to detect a rare disease, or if you're other examples where you're looking for a needle in a haystack, the best thing you can do is just always say no, and then you'll be right 1,000,000 times out of 1,000,001. So the way to handle that is usually you talk about ROC curves, or you talk about precision recalls, areas under the curve. Another way to do it is using the F1 loss that basically mushes together two concepts of the precision and the recall. Precision being what are the chances of detecting it, and the recall is how many, assuming that it is, will you find it? So obviously how many of these cases are out there is a big effect on these. And the F1 pushes it together, and so it's a somewhat complicated function of the true positive and false negatives. Which are defined as just counting. So how often did you say L is a specific class? The F1 score is defined per class. And there are different ways of summing it over multiple classes, but let's just talk about one class specifically. So L1 would be, yes, this specific pixel I has a label of L, and the ground truth is also the same thing. So the true positive counts how often this happens, and the false positive is if you said yes and the truth is no, and if you said no and the truth is yes. And this is a very unclear function that you'd optimize, because it's if L is continuous, then your function is basically piecewise constant, and it'll be basically impossible to optimize over this. So one way to do it, the way we did it, is, well, that's unclear. This is the inner product basically between L and G. If you know that L is all zeros and ones, and G, T, the ground truth is also 0 and 1s, the inner product between them will also give you the number. And similarly for the rest of them. And then if you let Li be the output of the softmax, basically the probability distribution, then you get a continuous function, which you can backpropagate through the network and get hopefully the optimum of this entire problem. And that's what we did. And that mostly helped for rare classes. These are going to be the comparisons. So they have two data sets. One is Weihingen and Potsdam. They're both in Germany. This is the state of the art as the time is 2015. They use multi-resolution CNN features combined with handcrafted features on the digital surface map, and then a Markov random field on top of that. And they get mostly better results in a lot of classes. On average, we're still slightly better, but only because we do much better on cars. And they haven't, they posted results, but they haven't published the paper yet. And they're actually doing probably better on most classes, but we're still doing better on cars. So on average, we're just slightly better. Actually, before this talk, I checked again. They posted more results, and they've improved their cars. So now they're always better. Oh, well. Okay, so this kind of feels like this should be the end of the talk. We have a problem. We presented a solution. We have good results. What else is there to talk about? And obviously, the problem is, I already gave you the spoiler, the amount of data. So if we now want to suddenly not work in Potsdam, our clients aren't interested in mapping Germany, we have a problem. We say, okay, go label 1 billion pixels. And the Academy usually starts the work there. It's like, okay, we have a data set. Let's work on the data set. Unfortunately, we have to pay our employees. So we don't like that. And we're going to try to do it differently. And our motivation is that the way we're training currently neural networks is not the way people learn. Professor Freeman had a nice talk this morning where he talked about how you can interact. So we don't just see flip cards, guess what they are, and move on. That's not how babies learn, even though it feels like it. And when he sees a dog, babies will generally try to touch the dog and run after the dog and poke its fingers in its ear and somehow interact. Like Professor Freeman, maybe they'll try to bang on them and see what sounds they make. And we want to try to somehow leverage that so that next time we see something, we'll be able to answer if or not this is a dog. This is a trick question. They're all dogs. Okay, so I don't yet have a grant for a robot that will poke dogs and bang on them. So instead, we're going to try to use, big surprise, the 3D model. How do I open it? All right, so this is a 3D model rendered. I'm sure it's not out of the ordinary in this conference to see something like that. This specifically is the Church of Nativity in Nazareth. There are aerial images using SFM and 3D reconstruction techniques. We create this model. And now we can use this as a poor man's replacement for wandering the world. And each pixel has more information than just its luminance or its intensity. And we can say something about where it is in the world, how far it is from its neighboring pixel. They're not always together in the world. There are depth discontinuities. We can talk about their normal. We can talk about their reflectance. We can reconstruct the lighting patterns. And we can put all of those into a much stronger representation where the problem of semantic segmentation will be a lot easier, classification, basically. So we're going to do that in 3D space. The features will include a planar segmentation, so we know how big the segment is, the normal of the segment. It includes the curvature, its local curvature, some very low-level pixels features from the image. It's almost embarrassing how low-level those features are that we took from the images. And we can do a pretty good job there. So the task is going to be done in 3D now. And instead of talking about labeling a pixel, we're going to talk about labeling a vertex in 3D. And since we're still being cheap on our labor, we're going to have only a very sparse annotation up here. Using a very simple interface, this can be done in literally 3 to 5 minutes, just choosing big blotches of ground and road and a few examples. And then the SVM classification, since there are far fewer parameters in an SVM task, this can be done with less data, and we can get a fairly good segmentation of the model. And that's what we're going to use. So the general flow, we have the 3D model and images, our 3D features, handcrafted, so 2012. We have our sparse user labeling. We do this, the semantic segmentation task in 3D. We do another 2 or 3 iterations there to save time on the user, so he doesn't have to label everything. He'll just label where the mistakes happened, where the SVM misclassified the vertex. And then this model we're going to back project onto the images. So basically we can generate nearly infinite amount of data of labeled images. Theoretically, we can also then create synthetic data, so we can reproject the models to different viewpoints. We don't do that because it's unclear how useful that will be. It will possibly just be generating the same data again and again, which won't be useful for the network. But we don't have to, because basically we have as many images as the camera can take, which is a lot. And we have labeling, and we can train the fully convolutional network. And now, hopefully, we can produce the same level, same quality of segmentation on a 2D image as we were able to on this 3D model. So it's a much harder task, and hopefully we can get to the same result. This is the confusion matrix in 3D using the SVM. Mostly diagonal. The F-score is lower. It's obviously not as good as a humanoid. It's an actual human. And this is the result on a single image. The results are very, very similar. There's a confusion between ground and road because the difference between them is mostly in the image, and our features are pretty poor. We can do better with the images, with the features extracted from the images. And obviously that carries over when we do it on a single image. New results that weren't fit into the slide. When we then do a 3D voting scheme between the images, we can we can run the classification on multiple images and then project them onto the model. That's the method of basically painting semantic classification onto the model, which Polyface this morning talked disparagingly about it. So that's what we're doing. And it boosts results by about 0.1 points. So it boosts the results to about 0.8. So that would make you think that a lot of the errors aren't consistent between images. So we tested a few different ways of averaging them, but honestly, just a voting scheme is the easiest, and it works pretty much just as well. So here are the results. On our data set, you'll notice that it doesn't look like Potsdam anymore. This is the classification in 3D, obviously projected back onto the image. This is the input to what the FCN would learn from, and this is the output of the FCN. They're pretty much undistinguishable. There's some blotchiness here between little plants in the ground. And road and ground, there's a confusion here you can see, where it's not consistent. One more result for the road. So that's the image, and that's the result. This is like a school and a yard. There's a problem of how do you want to label this. It's not quite ground, it's not road. So we followed ISPRS. We don't call it road, it's impervious surface. So anything that's ground level is called road, if it's not ground, like dirt. And once more, the Church of Annunciation, also from a single image, classification. And okay, a bit of credit. Besides the authors that we mentioned in the beginning, funding is important. It was funded by the OMA Consortium. And some of this work was done as a guest researcher in the Deep Vision Lab with Lior Wolf. And also thanks to Lior Uzan for helping me with the convergent properties of the F1 function. Questions?